Let's start with the next session. Next speaker is Elias. He will talk about immersed methods with and stage is yours.
Okay. Yeah, so thank you. So my name is Elias. I'm a PhD student from Chalmers University of Technology. And I've been doing my PhD for 4 years now, and I've been using Ferrite during the my entire study so far. And yeah, so what I do in my project is doesn't really exist in commercial softwares yet, so I kind of have to implement stuff myself using Ferrite and Julia. So yeah, Ferrite has been a really good, important tool for me and in my project. And today I'm going to talk about a thing I've been working on last year, and that's immersed methods. And so I'm going to talk a bit about what it is and how I've implemented it in Ferrite. So yeah, this is my intended content of the presentation. So first I'm just going to give an introduction about what immersed methods are. Then I'm going to give some examples of immersed methods found in publications and in research. And I'm going to talk about how I'm using immersed methods in my research. Yeah, and then I'm going to go into a bit of details how I implemented it in Ferrite. And I divide it into the 3 main stages of FD code. So pre-processing, solving, the solving stage, and the processing stage. Okay, so what is immersed methods? So one way I usually like to explain it is that it creates a simple way of creating a discretization for complex geometries by decoupling the mesh and geometry. So to kind of exemplify this, I here have an example geometry, a circle. And if we would want to mesh this or discretize this, we could of course just create a fitted mesh like this. But let's say for the sake of argument that we have a geometry that would be really difficult to mesh. Let's say it's a complex shape or something. Then what we can do is just create a very simple unfitted mesh like this. And so our unknown field, so let's say we have a displacement field, can still be approximated by this discretization. However, we have like an obvious problem here, and that is that the mesh no longer approximates the geometry. So we have like a decoupling of the mesh and geometry now, or the discretization and geometry. So we need to fix that in some way. So the main benefits with immersed method is that it's easy to generate meshes for complex geometries. So it's pretty much automatic, and it's pretty efficient, quick. The drawback, like I said, was that we need some new way of representing the geometry or respecting the geometry. And the way we do it in immersed methods is that the elements that are both inside and outside the domain, we have to create specialized quadrature rules that kind of respects the boundaries. So the elements inside the domain we can treat as normal finite elements, but these trimmed elements we need specialized quadrature rules. Okay, so that's the basic idea of immersed methods. So now I'll just show you some quick cool examples I found in literature where they use immersed methods. So these are not implemented in Ferrite. These are just in like the researchers' own in-house code. So there are many different flavors of immersed methods. Here is one flavor called finite cell method, and it's usually used by Ernst Rank and his team, coworkers. So in this example, they had a old archaeological dome, which was scanned. So they had it in like in a point data cloud. And this would, of course, be very difficult to mesh this structure because, yeah, it's pretty uncommon mesh format, so point cloud. So what they did then was just to immerse it in these very simple immersed elements. And then they so this was an adaptive simulation, so they could like adaptively refine where needed. And in this simulation, they did, I think, a principal stress analysis. So this is a pretty nice use case of immersed methods because it was difficult to obtain a normal mesh for this. Here's another example from one of my current or temporary supervisors, Clement Börjesson. So in this research project, they wanted to investigate the trabecular bone structures. So here they had like a scan data, which they first they couldn't use the scan data directly, so they needed to transform it into some new geometrical description. So they represented it as a level set function. And then with the level set function, they could perform this immersed methods here. So you kind of see the background grid here and the results projected onto a surface mesh. And according to my supervisor, he said that it first tried to mesh this with like tetrahedral elements, but it was kind of difficult to get good quality meshes, and they had problems with conditioning numbers. So they couldn't really use the iterative solvers they wanted in that case. So yeah, and in this case, the flavor of immersed method they used is called immersed geometric because they use isogeometric elements in the simulation. Okay, I research. So in my research, I analyze. I want to model meso-scale of fiber composites, and typically, the meso-scale of fiber composites are very quite a complex geometry. So it's quite difficult to obtain a nice, good quality FE mesh for that. So as an example, here is a composite with woven bundles together. And the bundles are typically kind of nice and well behaved, so that we can generate quite nice standard meshes for those. But the matrix is quite often it's difficult to obtain a good quality tet meshes. So the idea in my project is to exchange this tet mesh for the matrix and to use a immersed approach here instead. So we kind of just immerse the bundles in a matrix mesh. And that would, of course, like speed up the meshing procedure, and we could, we don't have to do the manual part. Another use case, in many cases, we want to do parameter study of the meso-scale, for example, change the thickness, and then we don't want to do this manual meshing procedure for each geometry in the parameter space. So then we can hopefully just use immersed method to generate discretization for all of them. So now on to some a bit more into detail. So I'm going to talk about how I've implemented immersed methods in Ferrite, and also go into a bit more theory about immersed methods. So I'm divided into just 3 main steps: so pre-processing, solver, and post-processing. So the biggest difference between a standard FE code and a FE code based on immersed methods is in the pre-processing step. So basically the mesh generation. So here's where I put like most effort coding wise. So just to exemplify, if we have this circle geometry again, we can embed it in a simple unfitted mesh. So this is of course very simple to do. And then the next step is to kind of trim out all the elements that does not belong to the boundary, to the domain at all. So that's a simple step. And then what we have to do is to create these specialized quadrature rules that respect the boundaries of the. And the way we do that is we have a octree approach. So this is the most common approach. So we zoom into a cell, and then we refine the boundary using this octree approach, maybe 1, 2, 3, 4 times. And then we have something that kind of respects the geometry much better now. And then using this subdivision, we can construct the quadrature rule. So these are basic 2x2 quadrature rules, and we do that for each subdivision, and then we aggregate the results into one one quadrature scheme. And yeah, so just to be clear, this is the mesh we do our computation on. This subdivision is not a mesh refinement, it's just a tool to generate the quadrature. So the benefits with this octree approach is that it works basically for any geometry. It's pretty robust. The drawback is that we get a lot of quadrature points for our trimmed elements. And so for big 3D problems, we can get up to maybe 10, 20, 30 million quadrature points quite easy. So that's a challenge. There are other ways to generating these quadrature rules, but this one is the most robust and most used. Another issue I have to mention that's pretty common in immersed methods is that we have problems with having elements that have very low volume fraction or small cuts. So for example, this element here have very low volume fraction, and so when we assemble the element stiffness contribution to the stiffness matrix, this will have a very bad conditioning number. And that can also lead to stability issues. So it's very important to have a solution to this in immersed methods. And the way we kind of do it, a pretty common way is to use something called the ghost stabilization approach. So I don't want to go too much into detail, but basically we add a stabilization term. So gamma here is a stabilization parameter, and we add this to the weak form. And this stabilization term is added on all interior faces of the cut element. So I kind of highlighted the interior faces here. And yeah, so the pre-processing step needs some way of finding these red interior faces. And basically what the ghost penalty term does is that it smoothens out gradients between two neighboring boundaries. So this cut element will, the high gradients we will get in this small cut element will be kind of smoothen out, and we get a much more well-behaved problem. And yeah, so this fixes the stability issues and condition number quite robustly. Okay, so this pre-processing step I've implemented in a package called Immersed. So don't ask me about the name, but it's still private. But if you want to use immersed methods after this presentation, you can just call me and then I'll give you access. So basically how it works is that there's mainly one interface function. So I call it immerse this, and you basically just give it the geometry. So currently it only works for surface meshes, but maybe in the future we can have level split function or point clouds or whatever you saw in the examples in the beginning. And then you give it basically the domain, position, size, and number of elements, and number of subdivision in this octree, and it creates this discretization. So you get out the computational grid, the cell quadrature rules for each element, and you get the ghost interfaces, and you also get the octree. Yes, so on to the next step, so the solving stage. So I didn't really know what to put on this slide because basically the the code flow is pretty much the same as a normal FE code. So the main difference is, of course, that you have a different quadrature rule for each element or each of the trimmed elements. So basically, the only thing you have to do is when you assemble the stiffness matrix, when you get to a new element, you have to create a new cell values for that element. And another quite neat thing is that since all elements are the same size, the Jacobian is actually the same for all elements. You only have to kind of re-init your base functions once. So that's it doesn't take that much time, but it's quite kind of neat. Yes, and then on to the last step, the post-processing. So here's quite this was kind of an interesting challenge. So like I said, the geometry and the discretization are no longer coupled. So in standard FE codes, we just take the mesh and we project or visualize or we export the results on the mesh, but we can't do that in immersed methods really. So we need some secondary visualization grid. So if this is like a plate with a hole here, and this would be the computational mesh, then we need to, whatever results we get on this, we have to project on some visualization grid that respects the boundaries. So kind of the way I did this, so here's some Ferrite code. So I output a DCK grid as usual, but instead of giving the computational grid, I have to give it the grid that follows the geometry. And then I can export displacements and stresses as normal, where the displacements and stresses are evaluated on the geometry. So it's kind of projected on. Yes, okay, so the last minutes here, I'm just going to show you some results. So here's just to get us started, a 2D example. So we have this plate with a hole here, symmetry boundary conditions, so we pull it on that edge. And I have generated a 35 by 35 grid. So this is what we do the computation on, and this grid here I'm just showing to kind of show the octree refinement. And yeah, so here's the stresses in X direction. We get this stress concentration here, and here I tried to make a just very simple convergence. So here is the stress, y-axis is the stress at this point, and x here is the number of subdivisions for this quadrature generation, or for the octree division. And you can see that after maybe 3-4, kind of have converged like this. Here's more recent results for in my project. So we had this 3D composite in the corner, and so I borrowed this from a colleague, and so they had already generated a tet mesh for this, and the story kind of was that it took maybe 3-4 days to generate a good quality mesh for that. So in this example, I just want to show you, here we exchange the matrix mesh, which is the difficult part to mesh, for you by using this immersed approach. So here are a number of different mesh sizes. And then of course we have to couple the matrix mesh with the bundle mesh in some way. We do that just using penalty method. And yeah, here's just some quick results. I'm calculating the membrane stiffness and the immersed approach and the pure tet mesh approach show good agreement with each other, so that's good. Yes, so just to summarize, I've showed you immersed approach, which provides a simple way of meshing your geometry if it's complex. Drawbacks is that you usually get a lot of quadrature points. So you typically need to parallelize your assembly loop. And I've implemented some pre and processing step in Immersed NURB. So if you want to use this software, you can hit me up. And then the solving stage can be done in pretty much vanilla Ferrite. Okay, thank you.
Okay, any questions? Yes. No, maybe Kim first.
Okay, you said that you do need to generate new cell values for these weird integration rule cells, and that makes sense. But does it even make sense to create these cell values, or is it better to just compute the values on the fly then if you can't really reuse them for the cell anyways?
I've tried both, and it doesn't really matter. So, but yeah, maybe it's just easier to reevaluate them each time. I agree.
No, Christopher?
Yeah, I have a few questions. The visualization grid, isn't that hard to, like, the point is it's hard to mesh the thing respect
yeah.
the boundaries. How can you do the visualization grid that has to respect the boundary?
No, so it could be like you don't have any requirements on the elements there. You don't have any requirements on the
Okay.
quality parameters basically, and you don't need maybe the interior elements, maybe just in the surface mesh, and then that's just a 2D. So you can, I think that's you don't have the same requirements for that mesh.
And then you said something, you had the same element size overall, but that has to be a bit restrictive. I'm just thinking if you have some part where you need to have small elements.
Yeah.
You have small elements everywhere, so you kind of need some hanging node stuff thingy or.
Exactly. So in the more.
Which I guess was the example you showed in the.
Yeah, in the examples they use adaptive elements. So then the size of each element isn't as big. But in Ferrite doesn't have adaptive stuff yet. But that's of course kind of important actually. Like you probably need finer elements in some areas. That's true.
Okay. Good.
But I guess it's a bit hard. But when you show this matrix fiber composite,
yeah,
is there any way to treat the actual behavior of the interface with this method, or is that just not possible?
I mean, yeah, you can treat it as.
But like the physical behavior of the interface, if you want to actually model the interface as a different behavior. I think now you had a penalty.
Yeah, but you can add cohesive zones and stuff like that.
Okay.
It's possible. Yeah. It's just that if I show you, for example, or to scroll. Yeah, so if you want some interface, let's say there's some material outside this and you want an interface between the, basically you will have a quadrature, interface quadrature rule, and they will kind of be inside the domain also. And there's nothing, no really theoretical problem with that, at least.
Then let's thank Elias once.